There's big dumb rocks. An ionic compound's just a mineral, right? They just come together. But the quantum model is going to drastically change our understanding of covalent compounds. And that's what we're going to talk today. We're going to start talking about, in our new understanding of orbitals, which is more complex than the previous one, how does that affect how we think about covalent bonds and the formation of compounds? So, lesson 1.4, bonding, day 1. Very cleverly named. I'm good at naming stuff. When my wife and I were naming our kids, we had a system where she would suggest ideas and I would say, that sucks. And then she'd say, what's your idea? And I'd say, I don't know, I don't have any. And then she'd bring another idea and I'd say, God, that's terrible. And then she'd say, well, what's your idea? And I'd say, I haven't really thought of anything yet. And this would go on for months on end. I'm very good at naming things. So, bonding, day 1. And we're going to start with what we call a basic rule, which is called the octet rule. If you remember that in grade 11, you learned about this. You even really learned about it in grade 10. It basically is that atoms must have 8 electrons in their valence shell. And this does comply with quantum theory because covalent bonding happens with s orbitals and with p orbitals. And if you look at the s block and the p block together, what do we end up with? How many electrons? If you look in one row at the s block and the p block, s orbitals hold how many? 2. P orbitals hold how many? 6, for a total of 8. 95% of covalent compounds, their bonding happens in s orbitals and p orbitals, so we don't have to think about all their electrons. We don't even have to think about all their quote-unquote valence electrons. We just have to think about the s and the p. Because if you think about it, D and F are always actually not in the valence shell. D and F, as a rule, are actually in previous shells, right? If the valence shell is 4p, then yeah, the d orbital is filled out, but not the 4d orbital, it's the 3d, so it's not actually part of the valence. Does that make sense? The valence shell, the outermost shell, if you follow the off-bow principle, that 1s, then 1s2p, or 2s2p, right? If you follow that, what you see is that when we're filling in the valence shell, it typically doesn't include the d orbital. The d orbital is from the previous shell. Does that make sense? Which means that the octet rule is largely going to be true. Does that make sense? S orbital holds 2 electrons. P orbital, 6 electrons for a total of 8 electrons. And this is the reason for the octet rule. Now, there are times when we can actually bond into the previous shell's d or f orbitals. Those are called expanded octet cases. We'll get to that. And even if we don't get to it, I'll actually give you a lesson that you can teach yourself so that when you get to university, you'll know it. Sometimes I have to not get to every lesson I like to teach in this unit. Just so you know, when I do that, I give you guys those lessons and sort of teach yourself if you want to make sure that you are as caught up as absolutely anybody. I like to make sure we get through the whole course. Some schools, they end up missing the last unit. I don't like that. But anyway, 9 times out of 10, the octet rule, it means, by the way, when we draw Lewis structures, we just do s and p orbitals. That's why even if we're drawing a Lewis structure of krypton, we don't draw 18 electrons in its outer shell. We just draw 8 because the middle block isn't actually in that outer shell. Does that make sense? The middle block, even if you do radon, which has not 18, but friggin' 22 electrons in its middle block, or 22 plus 8, 30 electrons in its outermost shell, or 32, sorry. We don't draw all 32 because some of those are in an f orbital, which is 2 shells down, and some of them are in a d orbital, which is 1 shell down, right? So when we draw a Lewis structure, we're always counting up just to 8, because when we draw a Lewis structure, we're drawing the valence s and p orbitals. Does that make sense? That's why back in grade 10 and 11, when you got bromine and you went to draw a Lewis structure, I said, don't draw 17 electrons, just draw 7. And at the time, I just say it just keeps it simple, right? We ignore the middle. But now you know why we ignore the middle. because the middle isn't actually part of the valence, right? For bromine, its valence is the 4s and the 4p. The 3d isn't part of its valence. Does that make sense? You can tell me if it doesn't. Now would be a good time. All right. So let's just make sure that we can look at this then. Magnesium, Mg. How many valence electrons does it have? 2. What about nitrogen? 5. Okay. And what about sulfur?
6.
Okay, good. How do we draw a Lewis structure of magnesium? Well, we use the symbol. What's the symbol for magnesium?
Mg.
Mg. And how many electrons would we draw on it? 2. And interestingly, we actually would pair these up because it's actually a full s orbital, right? So that actually adds a little bit of nuance to the Lewis structures we've drawn. To be honest, if you drew them as separate, I wouldn't care. But interestingly, the first 2 actually do get paired up, right? Because that's actually how the orbitals work. Energy level, magnesium has a full 1s, right? And then it has a full 2s, and then it has, and that takes how many electrons? Yeah, right, which if we're filling it out properly, it's not going to matter because it fills out, but it goes like that. And then what comes after 2p? 3s2, and it's got both of them, right? And if we wrote that out this way, we'd say 1s2, 2s2, 2p6, 3s2, or what's an even better way? Neon, and then 3s2 would be my preference, right? Okay. Take 2 minutes, fill that stuff out for the next ones. Just want to make sure we remember how to do that. And do it quick. When you think you've got one, come put it up here. This note's kind of designed, predicated on us not just having taken up the previous day's note, which makes me feel like maybe this is a little redundant. But you know what? Practice is always good, right? Practice makes perfect. So, you know, you get that practice and we get better at stuff. And like I said, when you've got it, come put it on my board, on my, what's that thing? Computer? Yeah. I know words and stuff. I'm not just good at naming things, I'm also good at knowing the names of things. Hello, computer. I will come to you. There you go, kiddo. Speaking.
For the magnesium, like Lewis structure,
Yep.
the electrons around it, shouldn't you have like given one to like technically you don't have enough, but like aren't you not supposed to bunch them up together?
So we actually, I mentioned that. That's what I'll mention it again. This is actually a case where we've actually learned a little bit more about how electrons get spread out. And the reason I put those 2 together isn't by accident. Why are they together? What orbital are those in?
S.
Yeah, they're in 3s, right? And in 3s, they actually are together. So the fact of the matter is all 8 electrons don't, it's not 1 to all 4 first. It's actually that the first one gets 2, and then the other 3 will get 1 each, and then start getting their pair. Now, I'm not going to be super finicky about that, but that's actually a better way to draw your Lewis structures. It's more correct. All right, so let's take a minute. Any questions from those? How do those look? They look pretty good to me. Anyone disagree? Susanna, did you put them both up?
Was I supposed to put
I don't
one?
care, that's fine. Does anyone want to fight Susanna because they think she's wrong, or are we good? Do I need to get the deathmatch cage out? I keep one in the back, so we're ready. Do I need to break it out, or are we good for another day? I got a pool cue in the back, I'm going to break it in half, like we're ready. But do we like those answers? Or have we all lost our voices and we no longer have the ability to speak?
That's good.
Oh, good. Okay. So, we're comfortable with that. Now, oh, thank you. I was going to come get it, but bless your heart. How does bonding happen? Well, again, magnesium and nitrogen will form an ionic compound. And we don't really need to say much about that. Magnesium has how many electrons in its outer shell? 2. And nitrogen has how many in its outer shell? 1, 2, 3, 4, 5, right? And how will they form a bond? Do they share? Is magnesium rich enough to share? Nah. So what kind of bond are they going to form? Ionic. Magnesium's going to give electrons away, and we get kind of an annoying number there because one magnesium doesn't have enough electrons to do it, so we need a second one. Unfortunately, that second one now has an extra electron, so we need another nitrogen, which will have 1, 2, 3, 4, 5 electrons. And the magnesium gives 1 electron to that, but it's still not there, so we need 1 more magnesium. And now it works nicely, right? And what do we end up with? We end up with magnesium with an empty outer shell. What charge will it have? What charge will it have? Plus 2, because it gave away 2 electrons. Nitrogen will now have 8 electrons, right? It'll be minus 3. Mg will be empty at plus 2. Nitrogen will have a full one at negative 3. And magnesium will have an empty one at plus 2. Now, worth noting, Mg2 plus has a different electron configuration, right? Mg2 plus has a full 1s, right? A full 2s, a full 2p. I have regrets. I'm going to write that below. I want to fit on the page. Guys, if you find that your stuff isn't fitting on the page, a little pro tip is you can highlight it. You can actually slide it back, and then you'll have and then you'll have more room to work with. Wow. Pro tip. So a full 1s, a full 2s, a full 2p. But does this one have anything in 3s? No, because what happened to them? It gave them away. And on the other hand, what about nitrogen with 3 electrons gone? What does its Lewis structure look like? So now nitrogen, negative 3, will have a full 1s, right? And then a full 2s, and then 2p6. Interestingly, what's actually true, this won't always be true, but in this case, what happens to be true about these 2 ions and their electrons? Yeah. So in fact, nitrogen and magnesium ions are what we call isoelectric. They have the same electron configuration. Iso, same. Electric, to do with electrons. Same electrons. Again, if you speak Latin, these two have same electrons. How's that feel? That's ionic bonding. They simply empty out their shells so that they always end up with a full s and p orbital. They always end up with a full octet. That feel okay? Feels good, right? Okay. That takes care of how covalent bonding happens. But what about, try that sentence again. That takes care of how ionic bonding happens. Great. Big dumb rocks. The magnesiums will be stuck to the nitrogens. Why are they stuck to each other? Kartik said it earlier. That was a hand. Was that not a hand? No, that was not a hand. Kartik.
Actually, I know this.
Yeah. Opposite charges attract. So a positively charged magnesium is going to be attracted to a negatively charged nitrogen. And in this case, you end up with a big crystal that is just a crystal made of nitrogen -3 ions and magnesium +2 ions in a ratio of 3:2, right? The formula for this would be Mg3N2, and our name for it, of course, would be magnesium nitride. Good. No need for any Roman numerals or anything because magnesium only can give up 2 electrons. Good. All right. Boring. Covalent bonding's exciting, goddammit. Let's take a look at it. Yay. So, when differences in electronegativity are lower, as general rule below 1.7, bonds may be formed by sharing electrons. Remember, who on the periodic table is able to share? The nonmetals on the right. Because to share your way to a full shell, you've got to already be at least halfway there. You got to be at least halfway there, right? Because it's a share of 1 to 1. So if I need 8 electrons and I only have 2 to share, the best I can get to is 4. That's not a full shell. So the poor don't get to share. Everything on the left side of the periodic table. Because remember, from a valence perspective, everything in the middle just has 2. They've just got those 2 electrons in the s orbital. We'll talk about why some of the ones in the middle give away 3 or 2 or 1. There's some weirdness going on there. But long story short, only the things on the right side of the periodic table, which we dub the nonmetals, are able to covalently bond. They can also ionically bond, and when they ionically bond, they are always taking, not giving, because the rich share with each other, and what do they do with everyone else? Take. And am I talking about atoms? Yes. Am I talking about also not atoms? Yes. But that's the way of the universe, right? So I guess rich people are just emulating the atoms from which they are constructed. So I guess we should, admire them or something. Low taxes for all. Anyway, so let's talk then about the formation of bonds between, let's say, 2 chlorine atoms. Well, chlorine, we said previously, has how many valence electrons? 7, right? In its third shell, it's got 3s2, 3p5 for a total of 7 electrons, right? So there would be the 3s2, and then 1, 2, 3, 4, 5. That's its valence. And if we have 2 chlorine atoms, here would be another one, 3s2, 3p1, 2, 3, 4, 5. And again, it's not super important, but notice how I actually filled it out. The first 2 were a pair. That's the 3s2. And then these I give 1 each in accordance with Hund's rule, and then the second one. I'm obviously not going to watch you fill this out, so I'm not going to know that you've done it that way, but it is noteworthy, right? And how do they form a bond? Well, we say that they're going to share these 2 electrons, right? They're going to share these 2 electrons. Tomorrow, we'll look at how their orbitals change to make that work. For today, we're just going to say that these electrons are in a 2p orbital, and they're able to actually jump between the p orbital of this chlorine and the p orbital of that chlorine, forming a bond between them. Now, we're going to learn tomorrow it's a little more complicated than that, but really only a little. It's not bad, I promise. And the way we usually draw this is chlorine bound to chlorine, and we draw the shared electrons as a line. We draw the rest of the electrons just as they are. Okay. That is easy to figure out for a simple thing. If I tell you to draw chlorine, easy to figure out. Where it gets harder is when we get to big, complicated structures, right? So I want to teach you a trick you can use to draw Lewis structures that will help you find the correct structure. We're going to start with an easy one that you probably don't need to figure out. In fact, we can go to the side here and say, right now, carbon dioxide, how is it going to form? And you'd look, and right off the hop, you can probably figure it out. How many electrons does carbon have? 4. 1, 2, 3, 4. And you're going to say, shouldn't we put those 2s together? Don't worry, we'll talk about it tomorrow. And then oxygen has 6, right? Sorry, what's that? God, stop being annoying. Anyway, you can probably figure out without doing anything how these are going to work. Can anyone figure it out? What's the sharing going to look like? Yeah, it's going to share here like that, right? Whoa. And then it's also going to share here like that. That's the worst drawing ever, but that's okay. And what we'd end up with is this structure, right? And carbon only has shared electrons, and the oxygens have 2 pairs that are shared, 2 pairs that aren't, right? Okay. But what if you couldn't figure that out? Maybe you could figure that out now, maybe you couldn't. What about when we get to something like the nitrate ion, which is a nightmare, right? It has an extra electron, there's 3 it's not easy to figure out. So today we're going to learn a tool for figuring out the Lewis structure of more complicated atoms. Is that fair? Okay. So these are the steps we're going to follow. And the first thing we're going to look at is we just want to look at the structure and say, okay, this is carbon dioxide. How many valence electrons does carbon have? 4. How many valence electrons does each oxygen have? 6. Okay? So that's 4 plus 12. So how many electrons do we have in the valence of this whole compound? 16. Because we're going to learn in this course that sometimes sharing isn't just pure sharing. Sometimes a bit of stealing happens in sharing. Sometimes in a covalent compound, one atom will, you ever like have somebody you eat dinner with and they eat a little bit more than would be a fair share? Anyone have a sibling like that? Or hypothetically a father like that? Where maybe there's 4 of you at the table, there's 12 meatballs in the bowl, and you think well, that's easy, everyone gets 3. And the first thing that clown does is take 4, hypothetically speaking. Anyone got someone like that in their life? We're going to find that sometimes atoms do that too. So this method is going to help us catch that behavior as well. Does that make sense? So the first thing we're going to do is figure out in this sharing arrangement how many electrons are there. And it only has the electrons it brings to the table. Carbon brings 4 electrons to the table. The oxygens bring 6 each for a total of 12, which brings us to a grand total of 16 electrons. Everyone comfortable with that? Does that feel okay? You can tell me now if you don't know where those numbers came from. Yep. It's okay. That's why we're here. That's why I'm teaching this. You don't know where they came from. Okay, no problem. If we were drawing these, if we drew carbon, what would its Lewis structure look like? We'd look at the periodic table and we'd say it needs how many electrons? 6 total, but in its valence. Its Lewis structure, 4. You'd go 1, 2, 3, 4, and you'd draw it like that, right? And then we'd look and say, okay, what should oxygen look like? And we'd count over, and how many electrons would it have in its outer shell? Awesome. 1, 2, 3, 4, 5, 6, right? And then we'd draw that twice. So if you want to draw them, by the way, go nuts. But to me, we can start to build the habit of just saying, if I were drawing carbon, how many electrons would I draw? 4. And if I were drawing oxygen, I'd give each one 6. Since I need 2 of them, that's 12 for a total of 16 electrons altogether. Because once they start sharing, all of these electrons can move around. That's what we're going to learn tomorrow, is that actually they don't stay in the orbitals they came in. They're actually going to move into different orbitals. But what we know is wherever they move, how many electrons are we working with? In this case, 16. Does that feel okay? Only the valence electrons are going to be involved until they're not. For now, only the valence electrons are going to be involved. So now, arrange the atoms, and if you're not sure where they should go, as a rule, the electronegative ones will want to get away from each other. So usually the least electronegative ones in the middle. Do we remember electronegativity? You don't have to super have it memorized. Long story short, the most electronegative thing on the periodic table is fluorine, up at the top right. The least electronegative is francium at the bottom left, right? So the closer to fluorine you are, the more electronegative, the further the less. So carbon in this case is further from fluorine, which means it's going to be our middle atom, and then the other ones are going to go around it. Does that make sense? As a rule, that's going to serve us well. Now, normally you'd do this all in one step. We're going to keep drawing this over and over again here so you can see it. Arrange the atoms with the least electronegative one in the middle and the other one surrounding it. 9 times out of 10, that's how it's going to work out. Sometimes it'll go other ways, but this is usually how it works. So if we're trying to get the structure right, this is probably going to get us there. Now, the first thing we're going to say is, okay, we know this is a covalent compound, so between them there must be at least one covalent bond. Does that make sense? So we're going to draw the covalent bonds. We're going to say, I don't know what this structure is, but I know for a fact that there's going to be at least one bond between everything, because otherwise it wouldn't be a covalent compound. It wouldn't be stuck together. Does that feel okay? Cool. Now, what we're going to do next is we're going to, again, normally you wouldn't redraw this, but the next thing we do is we add in all of the electrons needed, not to the middle atom, but to the surrounding ones. Keep in mind, how many electrons does the bond represent? Nope. 2. Once you form a bond, that's 2 electrons. It's shared between them, but it's 2 electrons. So how many more electrons does oxygen need here to complete its octet? It already has 2, and it needs to get up to an octet, which is 8. So how many more does it need? 6. And they come in pairs, so how many pairs? 3 pairs. 1, 2, 3 pairs of electrons. This oxygen, obviously, is going to also need... Nope, we're not doing that yet. What's the instruction say? Complete the octets around the surrounding atoms by adding lone pairs. So here's one of the surrounding atoms. So to complete the octet, how many electrons am I going to add? Another 6, which is how many pairs? Excellent. Very good. Now again, you might be saying, why am I doing all these steps when it's just carbon dioxide? And like Kartik said, I know we just need to put 2 double bonds. The answer is, if you can do this for a simple one, when you get to a hard one, you'll know what to do. Does that make sense? Because you're going to get to ones where the old rules don't work for you, but this process will work. Okay? Now, count how many electrons we have in the structure we just drew. All right? We're going to count how many electrons we have. So I'm just going to quickly redraw that structure like this. Oh, I did that backwards. And we have there, 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 and there, and there. Okay, count the electrons. 2, 4, 6, 8, 10, 12, 14, 16. We have 16 electrons. Is that enough, or do I need more? Remember, how many electrons do we have in this structure? 16. If I had room for more, I could just put them around carbon, right? But do I have room for more? That's all we have. So, if we had more electrons to work with, we could put them around carbon to complete its octet. But here, I can't complete carbon's octet with more electrons because I am out of electrons. So, now, to complete octets, you can move lone pairs to form double bonds. Does that make sense? So what we're going to do is we're going to move some lone pairs, and we're going to say, okay, how many more electrons does carbon need? Right now it's got 4, and it needs 4 more to get up to 8. So we're going to say, okay, these electrons here, they're going to turn into a bond. And these electrons here are going to turn into a bond. All right? We always favor double bonds over triple bonds. So better to take 2 electrons from each oxygen than to steal 4 electrons from one oxygen. We'll talk about why that's energetically favorable, but as a rule, double bonds are preferred versus triple bonds. So if you can make the structure with double bonds, that will happen way more often than you'll get triple bonds. And what we end up with then is now that's double bond like that, and this oxygen has just those 2 electrons left. I wouldn't normally draw them in this arrangement, but I want you to see where they came from. And this one has these 2 electrons left. And now, every atom should have an octet. Does that make sense? In other words, every atom should have how many electrons? 8. Let's count, shall we? Yeah, she's good. All right. Oxygen. How many electrons does it have? 2. Good. Carbon, how many electrons does it have? Full octet. Oxygen, how many electrons does it have? And if we add all those together, how many electrons do we have? 2, 4. So what we've created is a structure where every atom has a full octet, okay, and where the total number of electrons adds up for the ingredients we were working with. That's a proper structure. Does that make sense? Now again, for carbon dioxide, I probably wouldn't follow these steps. In fact, for carbon dioxide, these steps feel more confusing than helpful, don't they? You can be honest, that's okay. But these steps are going to be imperative because the next thing we're going to do is a polyatomic ion that you can't just follow the old rules. Because our usual rule is, as long as carbon makes how many bonds? How many bonds does carbon typically make? 4. And as long as oxygen makes 2 bonds, then everything will be happy. But with an ion, we have either extra, too many electrons, or we have too few, right? It's either a negative ion, in which case we have some extra electrons to work with, or it's a positive ion, in which case we're missing a few electrons. And at that point, the bonding rules go out the door. For a neutral atom, carbon's always going to make 4 bonds. But with extra electrons, maybe carbon gets the extra electron, in which case it doesn't need to make 4 bonds, it only needs to make 3. Maybe oxygen gets the extra bond, in which case it doesn't need to make 2 bonds, it only needs to make 1. How do you figure it out? And the answer is we're going to follow these same steps. Does that make sense? So these steps, probably a waste of time for carbon dioxide, but it was a good stepping stone for us to try the next one, which will be more challenging. Does that sound like a reasonable explanation? Or do I just sound like I'm full of it? All right, let's try it. Yeah. Tomorrow, no. No, I'll never quiz you tomorrow on something we did today. That feels unkind. You gotta have time to get good at this, right? And this is tricky. No doubt about it. This is tricky. So let's try another one. We're going to work on the nitrate ion. NO3 with a negative charge. NO3 with a negative charge. Which means that negative charge means we have 1 extra what? An extra electron. Therefore, 1 extra electron. And that breaks the world, because normally each oxygen would want to make how many bonds? 2. But we have an extra electron, so one of them maybe only has to make 1 bond, right? And then nitrogen normally makes 3 bonds, right? But because there's that extra electron there, maybe it'll only have to make 2, or maybe stuff will get weird. Does that make sense? And we'll talk about that in a minute. Things might get weird, all right? So let's take a look. The first thing we do is we count electrons. Well, we have a nitrogen here. How many valence electrons does nitrogen have? 5. Then we have 3 oxygens. How many electrons does each oxygen have? And if there's 3 of them, that is 18. Okay? But then we have a -1 charge, which gives us 1 electron. What's that sum to? 1 and 18 is 19. 19 and 5 is 24. So as we draw this structure, we have 24 electrons to work with. Does that make sense? 24 electrons to work with. Okay. Yep. That's right. And if it was a positive charge, it would? Beautiful. Exactly right. So you guys are doing great with this, by the way. This is tricky stuff. You're doing great. All right. As a rule of thumb, we put the lesser electronegative thing, the thing that's further away from fluorine, goes in the middle. So in this case, what's going to go in the middle? The 3 oxygens or the nitrogen? Nitrogen. So it's going to go in the middle. And we're going to surround it by fluorines, and I'm just going to we don't need to worry about angles yet. I'm just going to Sorry? It's oxygen. What I'm hearing is it's not fluorine. But I said the word fluorine a few seconds ago, so come on. Okay, so there we go. I'm going to use just kind of like a little triangle shape here. Whatever. We'll learn about shapes tomorrow. Oh, yeah. Oh, yeah. Get excited. No, shapes are fun. Not for me. I have terrible spatial relationships. Most people like this part of it. I'm terrible at I have trouble parallel parking. I'm not good with shapes, but you guys are going to do great. You'll be better at it than I am in no time. And then I'll feel embarrassed. Okay, what's the first thing we do now? Last time, we put the thing in the middle, and then we gave everything a single bond. So let's just do that here. We'll put the nitrogen in the middle, and we'll assume that there's a single bond to each oxygen like that. Does that feel okay? Okay. We're not going to make bonds between the oxygens. That could happen, but we're going to assume it's not. All right? That would be a weird structure. We're going to assume this is not a weird structure. Oxygen doesn't like to bond to itself if it can bond to other things, because things like to bond to things that are weaker than them. So oxygen would rather bond to nitrogen, which is less electronegative, than to another one of itself, which is equally strong. It's like me. When I go in the hall and I want to pick on somebody for lunch money, I'm not picking somebody the same size as I am. Oh, no. No. I'm finding a little kid, and I'm putting that kid upside down and shaking, baby. Give me my lunch money, by which I mean your lunch money, by which I mean my lunch money. All right? Nitrogen is going to give away its lunch money here. To whom? To oxygen. Okay. Now. Yeah, but as we know from last year, does oxygen like to share fairly? Be like me being like, kid, you got some lunch money there? Me too. You have $4? I have $4. That's $8. You go spend $1, and then I go spend $7. That's how oxygen works. Sharing. Share. That's what the rich do. This is what the rich do. All right. So, now what do we do? We add the lone pairs. Do we add lone pairs to everything? We'll add them to the surrounding atoms. Take a second and do that. Then I'll do it and we'll make sure we do it the same way. Add the lone pairs to complete the octets to the surrounding atoms. All right, so I'm gonna do this and say, okay, oxygen needs 8 electrons, so I'm gonna go like that. And oxygen needs 8 electrons, so I'm gonna go like that. This is good, right? No. Oxygen needs 8 electrons, so it says complete the octets. That's 8. I am not a girl. Nothing wrong with being a girl. Some of my best friends are girls, but I'm not a girl. Anyway, what's your thought? The line represents a bond, and a bond is really a shared pair of 2 electrons. So I just need 2, 4, 6 more, because this counts as 2 for a total of 8. Good. Which means I can do the same here. 2, 4, 6, and here 2, 4, 6. Oh my goodness, I can't believe I got it wrong, but thank you for you. And then, of course, I'm going to put 2 here, because nitrogen also needs a complete octet, right? We don't do it yet. We don't do it yet because we don't know that we have more electrons to work with. If you can add them to the middle if you want, you might just have to erase them later. Because what are we going to do now? We're going to count. Let's count. I'm pretty good at counting. That's what my grade 3 teacher said. I know most of you probably learned that in grade 1, but my grade 3 teacher, she said, Joe, you're so good at counting. Multiplication, not so much, but are you multiplying by grade 3? I think so. Yeah. Me, not so much. Anyway, I was a late bloomer in math. But then I bloomed and I was good. I ended up good, but boy, I was bad to start. It took me a while to discover. I was like a fringe gentian. You know what a fringe gentian is? It's one of these beautiful flowers that doesn't bloom until the snow comes out. And so it just looks like a stupid, ugly weed by the roadside all spring, all summer, all fall. It just looks like a big, stupid weed. And then snowdrops start, and all of a sudden, you got your fringe gentian. It's blooming. And you go, oh, it's so pretty. It's lovely. And so it's one of these things where you're like, oh, you're like a pleasant little surprise. And you imagine all the other flowers probably made fun of us, like, idiot, we're all blooming, you know? But you know what? Come wintertime, do you appreciate the hundreds of flowers that bloomed all spring? They're not doing anything for you now. But that fringe gentian, yeah, she's pretty. That's like me. Anyway, let's focus. Let's count electrons. How many we got? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. How many am I allowed to have in this structure? Not 42, not 74. Okay, we're going to get this. How many am I allowed to have for this structure? 24, is correct, right? If I needed more, where would I put them? Around nitrogen, which will happen, right? That will happen. But in this structure, does it happen? No. Okay, now the problem is I need to move around bonds to give me a stable octet. So I've got nitrogen, or this oxygen, does it have a stable octet? Okay, so it's happy. This oxygen, does it have a stable octet? It's happy. This oxygen, does it have a stable octet? Nitrogen, does it have a stable octet? Can I add more electrons? So how do I make a stable octet for it? It has to share. Now, as it happens, there's 3 possible things that can happen here. They happen with equal probability. Either this oxygen will make a double bond, or this oxygen will make a double bond, or this oxygen will make a double bond. Now, this is a symmetrical molecule. So does that make a difference here? Which one makes the bond? No, you could just flip it around and they're all actually the same structure. So in this case, it doesn't matter. There's still only one answer. Sometimes we have to say there's 2 answers. If it does make a difference, if we have what's called a chiral molecule, one that has a left-handed version and a right-handed version. You know, your left hand and your right hand look the same, but actually if you cut off your left hand, it wouldn't fit where your right hand goes, right? It can't fit. It's like I stupidly once was helping a friend who had lost the side of the side mirror, and I went to the junkyard and got a new side mirror, only I got the one for the opposite side. Can't fit it on. Doesn't matter what you do, right? So I had to go back to the junkyard and get the right one, right? Sometimes you'll have to say there's 2 possible answers, but here, really, we can pick any one of these nitrogens and it gives us the same structure. Does that make sense? So in this case, it doesn't matter which one you pick. Which one do we want to pick? Maybe the one I just circled? I'm going to pick this one just because I circled it, but you can pick whichever one you want. And we're going to turn that into a double bond, which means now nitrogen will be making a double bond to one of these oxygens. This oxygen will be making only one bond. That oxygen will be making only one bond. And if you note, this seems to break all of the rules that we've learned up till now, doesn't it? Up till now, we learned hard and fast rules. How many bonds is oxygen supposed to make? Oxygen's supposed to make 2. How many of these oxygens are following the rules? Only 1. 2 of them are breaking the rules, man. And how many bonds is nitrogen supposed to make? 3. But here it's having to make 4. Here's what happened. What did we introduce that let this get a little bit screwy? An extra electron. And what did the oxygens use that as an excuse to do? This oxygen took the extra electron, let's say. Right? This one's bonding like normal. This one took the extra electron, so it's now only having to make 1 bond. And then what did this one do? It took an electron from nitrogen. Nitrogen normally only has to make 3 bonds. But in this case, we forced poor nitrogen to make 4. So we actually took away one of its electrons that wasn't shared, and we're like, nope, 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 nope. Nope, that's mine. And then made it share all 4. See, that's what the electronegative ones do. And that's what this process is going to help you figure out. You would never have been able to figure this out just on your own. Does that make sense? You might have guessed your way to it, but you wouldn't know that it's it. This, by the way, adds up. We have 1 extra electron compared to what you'd expect from oxygen, nitrogen in that arrangement. But that makes sense because the charge is -1. And this oxygen is making 1 fewer bonds than normal because it took the extra electron. That adds up. This oxygen is making 1 fewer bond than normal, which seems weird, except this nitrogen is making 1 more bond than normal. We'll do a lesson called formal charges, where we'll learn how you keep track of all that oddities. But long story short, these oddities work. They make sense. So this is a stable structure. This is, in fact, what the nitrate ion looks like. So when you see nitrate in all those equations, NO3 -1, this is the actual ion. Can you see why we didn't have you draw this as a structure last year? Pretty confusing, right? But when you see the rules here, you can see that the more electronegative elements are able to get some extra electrons, the less electronegative take them.
We have veggie chowder for $2, and today's main entree is chicken teriyaki and rice stir fry for $7. Pizza for $2. $2 a slice, with chicken pizza for $3, taco salads for $4, and we always have French fries, Eagles. A small being $2.50 and a large being $4. That's on today's cafeteria menu. Make it a great day.
Aiden is such a good announcer.
And this is a reminder to all girls.
Don't tell him I said that because I never like to say anything nice about him, but you know, he's good. What's up? I wrote -1 on top because by rule, anytime a Lewis structure has a charge, we write it there. And we know that this whole thing has a charge of -1. Does that make sense? That's all. That's the reason why. Because we were starting right at the top with what ion? NO3 negative. Don't put this away. We got one more thing to write. Which is why I'm going to stop answering your questions. You can ask them tomorrow. Don't worry. Okay, now, types of bonds. A single bond is called a sigma bond. All right? A single bond is called a sigma bond. And the first bond between anything is always a sigma bond. So even in this double bond, the first bond between them is a sigma bond. Does that make sense? This NO double bond has two different types of bonds. The first one is called a sigma bond, right? And then the second bond between them is a different type of bond. And we call it a pi bond. Now, sigma and pi might give you a sense of what kind of orbitals are involved. I don't know. Anyway, I'll let you think about that. But sigma bonds and pi bonds. All right? So nitrogen here is making 4 bonds. 3 of them are sigma bonds. And that tells us it's down to 3 different atoms. Because the first bond between any 2 atoms is always called a sigma bond. But then it has 1 more bond. And any additional bonds between atoms aren't classified as sigma bonds. They're classified as pi bonds. If we go back to our carbon dioxide, carbon, how many sigma bonds, how many pi bonds? Yeah, these are sigma bonds. I don't like how that highlighted. I'm just going to draw with an arrow. I have regrets. Guys, I have regrets. We'll call these sigma bonds. That is a Greek letter sigma, by the way, though it's the worst drawn sigma you'll ever see in your life. And it has 2 pi bonds. Again, the first bond between any 2 things are the sigma bonds. So like when we drew this here, we were drawing the sigma bonds. And at this step where we had to make additional bonds, that's where we were forming the pi bonds. That actually mirrors how things actually bond, by the way. They form sigma bonds first, and then they form pi bonds. There's an order to these things. How's that feel? Not too bad? You do have some homework in here. I want this done. Try your best with it. All right? Try. But also study, because what do we have tomorrow? A quiz. Does it cover this stuff?
No.
What does it cover? Up to yesterday. If you have questions, what can you do? Ask me. All right? I'm working on getting textbooks for this class. Hopefully I'll have some for you by Monday. Have a wonderful day, guys. Be kind to one another. Don't do anything Kate Odette wouldn't do.